Today's experimental math seminar speaker is the one and only Sloane, the founder and president of the famous OEIS Foundation, who will speak about 8 lovely problems from the OEIS. A friendly reminder, the use of any electronic devices, including smartphones, laptops, etc., is strictly prohibited. Thank you very much.
What about your camera?
So this is based on contributions from a number of people. The way this came about is many of these problems I mentioned to the Sequence fans mailing list, and people got interested in them and sent in contributions, and then other people got involved and so on. So David Applegate, who lives in Maplewood, Lars Blomberg from Sweden, Andrew Booker from Bristol, England, William Cheswick, who happens to be in the audience, from New Jersey, Jessica Gonzalez from New Jersey, Maximilian Hassler, who lives in Martinique, I believe, Hans Haverman in Canada, Sean Irvine, who lives in New Zealand, Hugo Furtner, who lives in Germany, David Seal, who I think lives in England, Torsten Silker from Germany, Alan Wexler from Cambridge, Mass, and Chagua Wu from Yorktown Heights. So all of these people contributed in one way or another to parts of this talk, even if I don't mention their names again. I'm grateful for their help. And so I'm going to talk about 3 things. Originally there were going to be 3 parts to this talk, but the third part I will only mention very briefly. So counting intersection points, iterating various number theoretic functions, and Emil Post's tag system, which I was going to talk about, and then because of developments that haven't quite finished, and besides I had more than enough material otherwise, I decided to postpone it. But yesterday there was a development which made me want to mention it anyway. So this has to do with the foundations of computing. Emil Post, from the early 1930s, looking at a particular form of computation. He's looking at computation with binary words. And the particular tag system he's studying is you have a string of zeros and ones, finite string of zeros and ones. If it begins with a 0, you put 0, 0 on the end and drop the first 3 bits. If it begins with a 1, you put 1, 1, 0, 1 on the end and drop the first 3 bits. So you go from one string to another string. And then you repeat that over and over again. And the question is, can you predict what's going to happen? Or is this a really hard problem? Can you predict so after you've gone on for a long time, the string could become the empty string, it could die. Or it could go into a loop, or it could go on forever. Can you predict which of these 3 things is going to happen? And he couldn't settle this, and it's still an open question. And Marvin Minsky, in 1961, proved that with a different kind of tag system, different rules, you can mimic a universal Turing machine. You can do any computation you want by choosing the right system. But the question about whether you can do a universal Turing machine with this particular tag system is still open. Now, in order for this to be possible, there must be starting strings that live forever. We have not yet found one. Emil Post couldn't find one, Marvin Minsky couldn't find one, and various other people have worked on this. And Lars Blomberg in Sweden, on September 9th, has been looking at what happens if the starting string is 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, repeated k times. And if k is small, then it either dies or goes into a loop. If k is 110, so you've got a string of length 330, 1, 0, 0 repeated 110 times. That, after 4 times 10 to the 12th steps, was still growing. This is the first time there'd ever been a string that looked like it might blow up. It might go off to infinity. And the strings had reached length 10 to the 7th. Yesterday, he sent me an email saying it finally died. It reached the empty string after 14 days of computation. This many steps, 10 to the 14 or 15 steps, and a word length of 10 to the 7th.
So it's the longest living string so far?
It's the longest one, yeah. All the other, if you change k to, say, 99, it dies very quickly. The 110 is the first time it seemed like it might go to infinity. But we were very sad. I've been talking to Bill Cheswick about this. We were thinking this would be something that would be really worth attacking with serious computing to see if it really is going to live forever. Let's run it a lot longer. But we don't need to do that. It died, unfortunately. So this makes it pretty unlikely, I think, that this particular tag system will be a universal Turing machine. But it's still not ruled out. This picture shows how the length of the word grows. We start off with 330 bits, and we apply the tag system, and this is units of 10 to the 10th down here, and this is the length, and it goes up and up and up and up. And there's no repetition, it didn't go into a cycle, but then, slowly, it dies. So very sad. So the main part of the talk, the first of the main parts of the talk, is counting intersections of chords in semicircles. And this story begins 50 years ago, when I went to France for the first time, after 6 years as a starving graduate student at Cornell. And the first day in Amiens. And there are two things I remember distinctly. One is the food, in the first French restaurant that I went to in France, and the architecture. In Amiens, there's a cathedral, Notre Dame. It's one of the tallest, maybe the tallest of the tallest Gothic cathedrals in France, maybe in Europe. It's one of the great achievements of civilization, I think. And in there, unforgettably, are these rose windows. Just astonishing. So I've never forgotten that. And so we move to a sequence. A6561. The number, this started out at Bell Labs. Let me show the next one. About 1997 at Bell Labs in the Commons room. I put this on the blackboard as a question, an open question. Take a polygon with n sides, draw all the diagonals, and ask how many regions are there and how many intersection points. I'd found a paper by a Belgian astronomer who had tried to work out some of these terms. So I put it on the blackboard, and there were two visitors there at the time, Poonen and Rubinstein. And they worked on this, and they solved it. And in their paper, they give this illustration, which you can see is a little bit like a rose window. This is with 30 points. You have a 30-gon, a regular 30-gon, 30 points around a circle, and you join every pair, 30 choose 2 diameters, and you look at all the points, and there are 16,801 intersection points. So that's the 30th term of the sequence A6561. And the question is, what's the general term? And Poonen and Rubinstein solved this, and they found a formula. It's very complicated if n is even. If n is odd, you never get more than 2 lines crossing. And so the answer is n choose 4. But if n is even, you can have multiple intersection points. And if it's even, the very center will be an intersection of n over 2 diameters. Otherwise, you can have up to 7 diameters meeting at a point. So they have a very complicated formula. It involves a function. So, for instance, delta 4 of n is 1 if and only if 4 divides n. Otherwise, it's 0. So it's basically n choose 4, but then very complicated correction terms. And the first step in their proof, I think is worth mentioning. So they start off by saying, when do 3 lines meet at a point? So here are 3 chords of the polygon meeting at a point P, and they say, all right, let's study this. So they look at the arc lengths around the circle and convert them to radians. So capital U is the number of radians between A and F, and so on. So you have 6 radian measures, U, V, W, X, Y, Z, that add up to 1. And for this particular coincidence to happen, there's a constraint that you can write in terms of sines. So 3 lines meet at a point if and only if those 2 equations hold. So they did a change of variable and set alpha 1 to be V plus W minus G minus a half, and so on. And they ended up with what is called a trigonometric Diophantine equation. It says the sum, so if this happens, there are 6 rationals, alpha 1 through alpha 6, that satisfy that and that. And there's a paper by John Conway and Jones, which shows you how to reduce this to a standard Diophantine equation and how to find all the solutions. And that was the beginning of their analysis. So they were able to look at all possible intersections. And so that's old hat. Maximilian Hassler has made a very nice program that will produce these pictures on demand. And I said to him, I would really like to get colored pictures, like rose windows. And that seems to be very tricky. He did one by hand, but that's not quite my idea of a rose window. So the new stuff, problem 1b in this talk, is that somebody pointed me to an Austrian website called Zahlenjagd, which has problems, kind of fun problems. And the problem for winter 2010 says, I was going to read it in German, but my German isn't that good. So it says, given 10 points equally spaced on a line, over them draw all possible semicircles whose diameters are any 2 of the 10 points. So we've got 10 points on a line, we pick any 2 of them and draw a semicircle. And we do that for all 10 choose 2 semicircles. How many intersection points are there? It was a fun problem. And the answer is, well, if there were 6 circles, 6 points, then again, Maximilian Hassler has a program on the sequence. The sequence is A290447, fairly recent. You enter the number of points, and it will show you the picture. So this is 6 points, and there are 15 intersection points. And the reason is that is 6 choose 4. All possible choices of 4. Pick any 4 points. There are 2 semicircles, and they meet in a unique point. So for 6, it's easy. Up to 8, it's easy. For 10, there are multiple intersection points. And so the answer to the question is 200. And, so, again, this reminded me of Amiens, West Portal. This is the day of judgment. The souls come up out of the ground to be judged. It's not the same picture. It reminded me of it. And David Applegate looked at this, and he found a criterion for when to, for the coordinates of an intersection point of 2 semicircles. And if you have equally spaced points on a line with coordinates x1, x2, x3, and x4 in that order, then the intersection point has coordinates x and y, where x is a rational number and y squared is a rational number. So using that, it's easy to sort, to look at all the intersection points and sort. So he was able to work out the first 500 terms of this sequence, up to 500 points on a line. How many intersection points are there of the semicircles? But we don't know a formula for it. analog of the Poonen and Rubinstein formula. You do have the upper bound again. You can't have more than n choose 4, but there are multiple intersections and it gets very complicated. So here's a comparison of the two problems. Polygon, we have number of points, number of regions, and the number of k-fold intersection points. So there's plenty of data available. So the next topic, which has actually 8 parts, is iterating number theoretic functions. And so we're going to pick, and so there are 8 parts, but I'm mostly interested in the middle 4 or so. But I'll begin with the classical one. So the classical problem, if you look in Richard Guy's book, Unsolved Problems in Number Theory, UPINT, one of the questions has to do with aliquot sequences. So, and then there are 3 problems from Erdos that I'll mention: a Conway problem, an old problem of Helene, home primes, and another problem from Conway, which I would probably just very briefly mention. So the aliquot sequence, this is the classical version, classical problem of this type. So you look, sigma of n is the sum of the divisors of n. Sigma of 6 is the sum of the divisors of 6. It's 1 plus 2 plus 3 plus 6. It's 12. It's twice 6. It's a perfect number. If you subtract n itself, the sum of the divisors less than n is 1 plus 2 plus 3. If we don't count 6, the sum is 1 plus 2 plus 3 is 6, which is the number we started with. So that's a perfect number. So this is the function sum of divisors of n minus n. Let's call it S of n. And the question is, if you start with a number, say 30, work out the sum of the divisors minus n. So you add up 1, 2, 3, 5, 10, 5, 6, 10, 15, you get 42. Add up the divisors of 42. Repeat. After 16 steps, you get 0. But you might go into a loop. If you start with 6, that's a perfect number, so it loops. So Catalan, who is well known to this audience, Catalan conjectured that it would always have a finite trajectory. No matter what number you started with, it would either die or go into a loop. But in the sequence, which is A98007, which is the number of steps, so the number of steps for 30 was 16, the number of steps for 6 is 1. The current thinking is that most numbers don't die, they blow up. So there's an escape clause, we say it's -1 if the trajectory is infinite. And so the conjecture now is that most numbers blow up.
So Catalan was wrong.
Catalan was wrong, yeah. But we don't know of a single example where it's been proved that the number blows up. The first one that may blow up is 276. So its trajectory, where you iterate the function, take the number, replace it by the sum of the divisors minus the number you started with. So 276 goes to 396. And after 2,000 terms, it's reached a 208-digit number, which no one has bothered to factorize yet. But maybe there's no point. What we need is some theory behind this. Okay, so rather than try to write on the blackboard, I have a blackboard slide, so remember this. Phi of n is the Euler-Tosche function. It's the number of numbers less than or equal to n that are relatively prime to n. Phi of 1 is 1, phi of 2 is 1, phi of 3 is 1, and so on. Number of numbers less than or equal to n, sorry, phi of 3 is 2. Phi of p is p minus 1. The number of numbers between 1 and n that are relatively prime to n. That's phi of n. It's the product over all the divisors of n minus, of 1 minus n times 1 minus 1 over p. It has a kind of a dual, which is the Dedekind psi function, which is the same thing but with a plus sign. And in a minute I'll talk about this particular map. But first I want to mention another Erdos. So this is the first of 3 Erdos problems. Richard says that these are all discussed in a 4-author paper with Erdos and Pomerantz and 2 other people, but I couldn't find it in the paper, so it's not clear to me. I haven't seen anything by Erdos about this problem. Anyway, this is the first of the 3, where instead of the aliquot sequence, where you map a number to the sum of the divisors minus the number, this time we map a number to the sum of the divisors minus 1. So phi of the map 7 goes to the number of the sum of the divisors of 7 is 1 plus 7, which is 8. We subtract 1 and we get 7. So primes are fixed under this map. And there are the other 2, which I'll come to in a second. So here is the conjecture. Erdos apparently conjectured that you always reach a prime when you do this. Because it's monotonically non-decreasing, it's not going to go into a cycle. It can't go back down. It either keeps going up forever or it comes to a fixed point and stops. So for instance, 2, which is a prime, stops. The red means where we end up. So 4 goes to 6. 4 goes to 1 plus 2 plus 4. The sum of the divisors minus 1, which is 6. 4 goes to 6. 6 goes to 1 plus 2 plus 3 plus 6, which is 12 minus 1 is 11. 11 is a prime, we stop. That's the game. And this is the number of steps to reach a prime, and the conjecture is that we always reach a prime. And
is it subjective for the primes? It is true, or are there gaps that it misses a prime?
No, it gets all the primes. Yeah. But the numbers that live for a long time before they die, before they reach a prime, are these numbers, 2, 4, 9. These are the record holders for the number of steps before they reach a prime.
Can you get the same prime 2 different ways?
Yes, sure. Yeah. So these are the numbers that they take a long time to reach a prime. And I don't know what they are. What are those numbers, please? So you can say 292, 114. What's special? What else is special about those numbers? How would you identify those numbers? They've got to have some magical property, probably. And do numbers always reach a prime? All right, problem 2c. There are 3 Erdos problems, and more interesting as we go along. The first one is a strong conjecture that we always reach a prime. The second one is we have examples where we don't reach, which blow up. So the second one is we take the sum, we're iterating the following map. K goes to the Dedekind psi function of k plus phi of k divided by 2. Iterate that, what happens? So here it is spelled out, and you can see that if you have a prime power, it's fixed. Otherwise, we grow. So either we keep growing forever, or we come to a prime power and we stop. But now, the interesting thing is, we can increase forever, and we can prove it, which is very rare in these iterations. There's actually a proof that. So here's the proof. This is R.C. Wall, 1985, a short note in the American Math Monthly. I don't know quite exactly which numbers he looked at, but 45 is the first number that blows up. And the proof that it blows up is very nice. I'm going to prove, he proves, that 1488 blows up forever. So if you start with 1488 and apply this map, 1488 itself is 16 times 3 times 31. You apply the map once, and you get 16 times 3 times 37. Then you get 16 times 3 times 44, 16 times 4 times 41, 16 times 2 times 83, 16 times 167, and 16 times 5 times 67 over 2. I've written them all with the conspicuous 16 in front. Here we've actually lost a factor of 2, but that doesn't matter, we pick it up at the next step, because the next step we have 32 times 3 times 31, which is twice what we had 7 steps ago. And that repeats. So from this point, well, for this trajectory, starting at 1488, it doubles every 7 steps. So obviously it's unbounded. If you start with 45, after a while, that's the first of the ones that blow up. After a while you get 1488, and then it blows up. And all of the ones up to 147 contain 1488. 152 is more complicated. 152, I looked at the factorization of this, and you see lots and lots of primes, and as the trajectory increases, the primes sort of fade away. And after 389 steps, you get 2 to the 104 times 3 times 31. And 7 steps later, it's 2 to the 111 times 3 times 31. So we join, these two trajectories meet. And so from 389 onwards, the sequence started at 152 is 2 to the 100 times this sequence. So does that always happen? I didn't have time to look at it. If someone wants to do a little calculation just to see. Is it true that no matter what you start with, you always meet the trajectory of 45? Do they all come together eventually? So here is this one, we actually have trajectories that go to infinity. Right, the third of the Erdős ones. We're now going to iterate the function. You take the sum of the divisors plus the phi function and take the average. And I've got a bigger version of this is on the blackboard. So my blackboard size has a black border. So 1, 2, 3, primes are fixed. 4 goes to 9.5. So the map is, we take the sum of the divisors. Sum of the divisors of 4 is 7. 1 plus 2 plus 4. The number of numbers less than or equal to 4, prime to it is 3. So 4, it's 2. So we have 7 plus 2 over 2. 9 over 2, 4.5. It's not an integer, so we die. So 4 goes to 9.5. In one step, it died. And the red indicates that it died because it got to a fraction. On the other hand, 6 goes to 7. 7 is a prime, so it goes to itself. So in one step, it terminated in the fixed point. So you can do this for all the numbers and see what happens. And 270 doesn't seem to die. It seems to be immortal. So I should say the calculations for this on this problem were made by Hans Habermann, Sean Irvine, and Hugo Pförtner. Pretty extensive calculations. And here's what we know. Here are some of the things we know about this problem. So, if you start with 1 or a prime, it's fixed. Good. A useful fact is that sigma of n plus phi of n is odd if n is bigger than 2. It's odd if and only if n is a square or twice a square. So if it's odd, it dies. So if we start off with a number which is a square or twice a square, we die in one step. We get a fraction, an odd number over 2. So that dies in one step. But some numbers continue for a while before they die.